Good afternoon, ladies and gentlemen, also from my side. So I'm Esko Tahkola, coming from Messrs. OI, which is acting here in Scandinavia as the CIDRA corporation. And my topic today will be about flow measurement, about the only flow measurement principle developed in this year 1000, so the passive clamp-on Sonatrack, which is providing actually much more information than just the flow information for the user. So I try to highlight that side now for you. A couple of words about CIDRA, which is behind this technology. Company comes from America, Connecticut, and the first area where it developed products was oil and gas, and now we are serving several industries listed here. If we look at the flow measurement principles, the old ones are listed here, and now we do have a new principle, which is array-based sonar measurement principle. In addition to flow velocity, we can, with the same device, measure also the volume occupied by gas bubbles within the pipe. And based on that, we correct the errors those bubbles are causing, of course, for the volumetric flow measurement, but also for the density measurement. So you get more accurate mass balances. We do have also an immersion version of that, so a gas hold-up meter, what you can put into the separation zone of a flotation column and optimized flotation there. The product is consisting of a sensor band that is wrapped around the pipe, sensor cover that protects that band, and a transmitter that is then connected to your system. Installation is simple. You just clean the pipe, wrap around the sensor, and tighten it. So the process can be all the time on, and the total installation and commissioning time is typically 2 hours. In addition to that, we do have a USB interface. By that USB stick, you can take an electrical copy of the measurement, and that enables remote location technical support based on that. You can clamp it on any pipe, not hoses, so pipe has to have an even outer surface and solid walls. The principle is such that we are tracking the pressure spectrum generated by the turbulence front that every flow is generating when it's propagating in the pipe. That turbulence front is pushing a little pressure against the pipe inner walls, and we are picking up that pressure spectrum with our sensing zones and just simply measuring the time of flight between sensing zones when that propagation is happening there with the flow velocity. So from that we get simply the flow velocity, and by introducing the diameter we can calculate the volumetric flow. So it's very easy to understand that it doesn't matter what is flowing there, only it's flowing and generating those variations, so it's providing us this information. Now we go to that entrained air measurement, so the gas bubbles. And that we do by measuring the speed of sound in the pipe to both directions. So speed of sound in a material is got by this formula, so it's the compressibility divided by the material density and square root out of that. And if we think about liquid-based materials, immediately when you have a little bit gas bubbles there, the compressibility is changing a lot, even though that the density is not much affected. So it makes this speed of sound a very sensitive function of gas bubble volume. And we simply measure that, and in addition to that measurement, we need some kind of information what is the process line pressure, because that's affecting the density of that gas in those gas bubbles, and thus to the speed of sound. So also, this one is a clamp-on measurement, so the same device, just in software option. How do we utilize it to correct the density gauges? Here, an example: if we do have a slurry flow with a specific gravity of 1.4, with absolutely no gas bubbles in there, so of course the density meter is showing this value. But if we introduce some bubbles there, let's say 10% of the volume, we can see that the change is quite big. So this density meter will show now 1.26, which means 28% change is in your production rate or in your mass balance. Quite a big error. And that error is, of course, then dependent on that what is the specific gravity of your slurry. The closer that slurry is to the water density, the bigger is the error caused by 1% of gas bubbles in the flow. So if you are there having something, a specific gravity like 1.1 or something like that, so 1% is causing 10% error in your mass balance. If the specific gravity is 1.5, then 1% of error is causing 2% error in your mass balance. Because people are not seeing the error, this is often not paid attention in processes and their controls. We also get diagnostic info on the flow model within the pipe and how it behaves, and also information from the other process. So the turbulences that are basing signal tell about how the flow is behaving in different situations in the pipe. Is it a fully developed turbulent flow? Is it tilted flow velocity profile? Is there sanding happening like this? Based on this, we can optimize this flow measurement to operate optimally, even in very difficult piping configurations and flow situations, and inform the customer on what is happening there inside the pipe. So if we look at how it works, so if we take a certain size of turbulence, we get a response of that at a certain frequency which is comparable to the size of that turbulence. When you change that one, the size, so we get a response on a higher frequency and so on. We make a map, putting the frequency on the vertical axis and the wave number in flow direction to this axis, and the intensity distributions are forming a front on this map. And from the shape of the front, we can define what is the flow model, and because we do have frequency here, 1 per second, and wave number here, 1 per meter, the slope of this line drawn along the maximum intensities tells us directly that at what velocity each size of turbulence is propagating there inside the pipe. Very simple and effective information for the user. So we can install in places like this and still get a very good high accuracy and repeatability for the measurement. Here we can see example how that kind of ridge looks like in a position where we have installed very close to the pipe. So we can optimize the measurement by choosing these frequencies what we are utilizing for the final calculation. We can also see if the solids are flowing with a slower speed than the carrier liquid. So here we see a situation where the solids are forming already their own intensity ridge. This of course causes density pulsation in the process and blockages of filters and even blockages of pipes by sedimentation. So basically we are getting by this device diagnostic info on the flow and process. It measures also the gas bubble volumes, and we can correct the errors those were causing for density measurements, so we get better mass balances. We also know that when air is part of the problem in the runnability of the process, because we can measure that separately. We would like to have turbulent flow or shear thinning pastes or plug flow. And we need some kind of minimum flow rate, and that is depending on the flowing material and its flow model on low flow rates. And the minimum flow rate is between 0.3 and 0.9 meters per second. We would like to have a full pipe. Of course, we can measure the gas bubble volume. So in vertical pipes, the air will be in bubbles. So those ones we can measure up to some air content, but preferably full pipe. The capital cost is somewhere between magnetic flow meters and Coriolis meters. Life cycle cost is less than either because it lasts longer than the pipe. We have customers that have changed already 3 times the pipes and still the same measurement with same configuration working there. It's non-invasive, doesn't wear, doesn't need any kind of maintenance. No, there's no process downtime for the installation. So, pretty good device. And it works with practically any fluid, even gases, liquids, multi-phase flows that include these gas bubbles. It also works with scale buildup. Of course, it measures the flow velocity correctly. Of course, the volume of the scale will be a tiny error in the inner diameter definition when you are calculating finally that volumetric flow. But we do have customers that have developed models for the growth rate of the scaling, and thus they are modifying the inner diameter as a function of time. And instead that they earlier had to clean the pipes once a month, they are now cleaning once a year or once in 2 years, which means quite a lot of more production time. It works practically with any pipe. The pipes can be lined even on outer side and inner side, doesn't matter. And it's immune to the effects of magnetic ore, which is a problem for the magnetic flow meters because the magnet field generated by the ore is causing an error to those ones. And the key thing is that it doesn't drift during the lifetime of the device. So your process optimization on production rate controls is on stable basis throughout the lifetime of the process. And that's very important when you are thinking about the practical situations where the laboratories and operators are arguing that which is correct. And here we see some examples of global users in mining. So over 250 mining companies. We just lately passed over 500 mining locations using these ones globally. So it's been penetrating that market very shortly and favored solution for end users. So thank you for your attention here, and welcome to meet us and discuss at our CIDRA stand number 221, very close to this when you go out from this door. Thank you.